Today we're going to look at vertically stretching and compressing quadratics. And so far what we've talked about is we've talked about shifting, moving the graph right, left, up, and down. Then we talked about reflecting the function. So we either reflected the graph over the x-axis or we reflected the graph over the y-axis. And specifically we're relating these two quadratics, to parabolas, to the U-shaped curve. And now what we're going to look at today is we're going to look at stretching or compressing. So stretching, remember, we're going to elongate the graph. And compressing means we're going to shrink or compress the graph. And you may want to use colored pencils for this one as we look at our first example. Because what it says is, consider this quadratic function, f of x equals x minus 2 quantity squared minus 9, which is the picture that's drawn on your paper and on the screen here. And then it says the quadratic function g and h are defined by g of x equals 2 times the function, and h of x is 1/2 times the function. And first of all, what it says is, in part A, it says label the graph shown as f of x. So up here on my paper it's blue, but that's f of x. There's our function. And again, you might want to draw this in color or whatever works for you on your notes. But on part B here it says, on the graph, in a different color, create a graph that is vertically stretched 2 times that of f of x. Well, in order to do that, what we do is we're going to multiply the y coordinates of each point by 2. What I want to point out is that we're only multiplying the y coordinates. So our first point at the far left here, this point is negative 1, 0. We're going to take 0 times 2 and get 0. The point 0, negative 5. We're taking the y value of the point, which is negative 5, and we're multiplying that by 2. Well, negative 5 times 2 is negative 10. The next point, which is 1, negative 8, we're going to take the y value of that point. Negative 8 times 2 is negative 16. The vertex, or the turning point on this graph, is 2, negative 9. We're taking the y value of that point, negative 9 times 2, which is negative 18. The next point is 3, negative 8. We're taking the y value of that point. Negative 8 times 2 is negative 16. The point 4, negative 5, we're going to take the y value of that point, which is negative 5, times 2, which is negative 10. And the last point given on this graph, we have 5, 0. We're going to take the y value of that point, 0 times 5, 0 times 2, which is still 0. And what we're going to get when we draw this picture here for our g of x function is we're going to get a vertically stretched graph. So now, let's create the graph that's vertically compressed by 1/2. So we're taking my original picture on your paper and we're going to vertically compress it by 1/2. And what we do when we're dealing with that is we're going to multiply the y coordinates of the blue graph, the given graph, by 1/2. So when we go back here, again, we're only multiplying the y values. Our first point is negative 1, 0, and 0 times 1/2 is 0. Our second point, which is the y-intercept on this graph, 0, negative 5. Negative 5 times 1/2 is negative 2.5. On the original graph, we have the point 1, negative 8. Negative 8 times 1/2 is negative 4. The vertex is 2, negative 9. The y value, negative 9 times 1/2 is negative 4.5. The next point, 3, negative 8. Negative 8 times 1/2 is negative 4. The point 4, negative 5. Negative 5 times 1/2 is negative 2.5. And our last point, 5, 0. 0 times 1/2 is 0. And when we draw this function here, which I'm going to call h of x, there's our vertically compressed graph. What points did not vary? When f was vertically dilated by factors of 2 and 1/2. Before we answer the question, let me point out that dilating, if you think about going to the eye doctor and they dilate your eyes, your pupils get really big. Well, in math, we could get bigger with the word dilation, or we can get smaller with dilation. And what points did not vary? Well, the x values. Did not change. And the reason is because they are horizontal. Or I'm going to put they are a horizontal factor. We only changed the vertical. We did not change horizontal. So when we fill in our chart here, and there's nothing to fill in on this, but we'll pull out our transformation chart momentarily. But the function h of x equals c times f of x. So when a number is out in front of the function, and that number is greater than 1, we're going to vertically stretch the graph. And when the number out in front is between 0 and 1, so it's a fraction, then it's going to be a vertical compression. And let's go to our transformations chart, and let's fill in those last two pieces on this chart. Which are here. Same thing that we just had on our notes, but hopefully this paper is all-in-one guide for you. Again, when c is in front of the function, this means that we have a vertical stretch. And in particular, that's when c is greater than 1. And if c is greater than 1 and it's a stretch, when c is outside the function and it's between 0 and 1, that means that it's a vertical compression. And in terms of the vertical changes here, what happens is that the c is considered to be outside of the function. if you are planning to take pre-calculus, the horizontal stretch and compress will be inside the function. Just as a little aside there. Again, we're not going to deal with horizontal in Algebra 2. We'll deal with it in pre-calculus. So when we flip back to our notes, and we're going to turn the paper over. So as the graph of y equals f of x is shown below, consider the function y equals g of x defined by g of x equals 3 f of x minus 2. And it says, what two transformations have occurred to the graph of f in order to produce the graph of g, and specify both the transformations and their order. Well, in terms of order, we read a book, we read the pages left to right, we read an equation left to right, so we do the transformations from left to right. The first transformation is coming from the fact that we have a 3 out in front of the function. It's outside the function. That's going to be a vertical stretch. And I'll put a 1 by that. So that's going to be the first one. Minus 2 is our second transformation. It's also outside the function. And it means that we're going to go down 2. When we come over here to draw the graph, I want to put some points on the graph. Here, 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 here. And there's more, but that'll help us enough. And again, left to right is the key. So the first thing that says to do is it says to vertically stretch. So I'm going to vertically stretch it, and then I'm going to move the graph down 2. You could do both in one, but I'm going to do it in 2 steps here. So the vertical stretch, once again, like we did on the front page, is we're changing the y value. If we look at the points on the left, our first point is -5, 3. We're going to multiply the y value of that point, 3, by 3. So 3 times 3 is 9. Our second point on the graph is -4, 0. We're going to multiply the y value of 0 by 3. But 0 times 3 is 0. Our vertex is -3, -1. -1 times 3 is -3. 1, 2, 3. -2, 0 is the next point on our graph. 0 times 3 is still 0. And -1, 3. Well, 3 times 3, because we're taking the y value only. 3 times 3 is 9. And all that we've dealt with so far is we've dealt with the vertical stretch of this function. But now that we've dealt with the vertical stretch, we can finish by moving the graph down 2. So we're going to move it down 2. So we're going to take this point over here, -5, 9, and we're going to move it down 2. We've got this point, -4, 0. We're going to move it down 2. We've got our vertex. We're going to move that point down 2. -2, 0. We're going to move down 2. And -1, 9. We're going to move it down 2. And now we've accomplished both of the transformations with this black graph here, which I'll call g of x. next one should be short here. If the quadratic function g of x has a y-intercept of 12, which of the following is true about the function h of x equals 3 g of x minus 5? Well, to figure this out, we need to do the math behind it. So this says 3 times g of x. Well, 3 times 12 equals 36. And then it says minus 5. Minus 5, which is 31. So here we showed our work to justify our answer. It has a y-intercept of 31. And to finish, kind of like the problem at the top of our page here, it says on the graph of f of x below, sketch a graph of 1/2 f of x. So this time we're going to vertically compress the graph. And then when we get over here to the right side, then we're going to do something else to it. But let's deal with the left side here first. And once again, when we vertically stretch or compress, we're only changing the y values on these graphs. We take a look at this one here. Then start to the far left. That point is 1, 2, 3, 4, -5, -3. -3 times 1/2 is -1.5. The point 1, 2, 3, 4, -4, 2. Well, 2 times 1/2 is 1. The point -3, 5. We'll take 5 times 1/2. 5 times 1/2 is 2.5. Our vertex. Our vertex is up here at 1, 2, 3, 4, 5, 6. Half of 6 is 3. The point 1, 5. We're taking the y value, 5 times 1/2, to get 2.5. Our y-intercept, which is 0, 2. 2 times 1/2 is 1. And the last point on here is 1, -3. Well, half of -3 is 1 and 1/2. And I'm really sorry, the board is disoriented. I'll do my best to get a good picture, but I think it's going to be weak. And not to disappoint, it's pretty weak. So hopefully you were drawing with me, or filling in those points, and have a much better picture than I. But when we finish this now, we look at our right graph here. It says 1/2 f of x minus 2. We've already dealt with the 1/2. That's our vertically compressed. What does minus 2 inside of the function do to our function? We're going to move our graph right 2. So we're going to take that blue graph, my very terribly drawn blue graph, and we're going to move it 2 spaces to the right. So I'm going to look at my points over here. 1, 2, 3, 4, 5, -1.5. -5, -1.5. We're going to move it to the right. It's going to land here. It's not quite so disoriented over here to the right, so I'm lucky on that one. The next point is -4, 1. We're going to move it 2 to the right. We have this point -3, 2.5. -3, 2.5 is going to move 2 to the right. Our vertex, -2, 3, is going to move to the right. It's going to become the y-intercept now. That's 0, 3. This point -1, 2.5 is going to move 2 spaces to the right. So going to be positive 1, 2.5. Our blue y-intercept at 0, 1 is going to move to the right. And finally, our point 1, negative 1.5 is going to move to the right. And now what we have is our completely graphed function. My red graph much better than my blue graph there. And this is the 1/2 f of x minus 2.